Welcome to Addenda 3. This is another one of the added-on lessons. I'm kind of covering some things that we assume that you will know in college algebra in our Math 135 course. But you may not know it, or you may not feel terribly comfortable with it, or you just might want to see my crazy take on it, whatever. So what we're going to do is we're going to explore the complex number system. And the complex number system is the set of all numbers currently known to mankind. Okay, so let's take a peek. By the way, if you want an accurate history, here is one source you might check, Math Through the Ages, A Gentle History for Teachers and Others, and I have the authors there. Howard Eves has a great history of mathematics, and there are other wonderful sources, because I'm going to make a totally fictitious history here, but play with me, okay? So how did we start with our numbers? Well, it kind of makes sense that in early mankind times, or humankind times, I might look out there into my little green area and see 1, 2, 3, 4 rabbits. And I might count 1, 2, 3 pheasants. Now, because I like counting those, they happen to be called the counting numbers. So in the Patty Blanton distorted history, the counting numbers would be the first ones with which we become familiar. And then, of course, once you find these numbers, then we can do things like how many animals in all do I have in my yard? Well, 4 plus 3 is 7. Oh, hey, by the way, I'm writing in what's called Hindu-Arabic numerals, and they came much, much later. Really, especially for those of you that might be kind of history buffs, oh, there's some wonderful stuff as to all of this development. I might add my counting numbers. 4 plus 3 is a total of 7 animals that I'm looking at. I might subtract and say 4 minus 3, I have 1 more rabbit than I do pheasant. And of course, if you have rabbits around, you're certainly going to multiply, right? So there's multiplication, there's division. So we start out, it makes sense that probably humans first came upon the counting numbers as we wanted to count things around us. Well, now here I'm definitely very wrong in my history, but I want to do this for a reason. So one day you get up and you discover that, oh no, my animals have left. So how many animals do I have? 0. As it turns out, while 0 seems like such an easy concept for us, there's quite a big history about 0. In fact, there are some books that are just about the number 0. But if we add 0 to our counting numbers, they really are called counting numbers or natural numbers. 0, 1, 2, 3, 4, and so on, those are called our whole numbers. And of course, the mathematicians had to decide, well, how do we add? How do we multiply? Ooh, and what about dividing with that 0? You're going to hear a lot about that. So, while 0 did not really come about next, probably in our history, I wanted to bring that up next. Well then, maybe things haven't been going so well and your family's a little hungry, but the neighbor has a whole lot of fish, so you borrow 5 fish with the understanding they're on a loan. Well, not those particular ones, but you owe your neighbor 5 fish. So that makes you think of the number -5. Okay? So if we then have negatives, the idea that we could be owing, and of course if we have a 0 and we drop below that value, we're in a negative territory. So if we get all of the numbers, -3, -2, -1, 0, 1, 2, 3, and so on, all of those numbers, including my natural numbers, my whole numbers, and then all the negatives, those are called my integers. Okay? So now we've got, quite a few numbers here to be dealing with, obviously infinitely many. Okay? And then we decide, there's a mammoth that's being just a little bit too tough on the neighborhood, and that's meat for a long time. So a whole group of people go out and decide to take down the mammoth. So sorry if I've offended you. But then you might decide that since there were 12 people, that each one of them gets 1/12 of the mammoth. 1/12. Oh, well, now we're dealing with fractions. And once you start including all those fractions, you have the set of numbers called the rationals. Now, I forgot to mention back on the integers, you might recall from pre-algebra days and algebra 1 days, how do we add negative numbers, -4, how do we subtract -5? We have rules for that, right? What happens when I take a -2 times a -3? We'll come up with all those rules. In the case of rationals, with our fractions, what's 1/2 times 14? What's kind of interesting is it's pretty easy to add fractions if they're the right kind. 1/2 plus 1/2 is 2 halves or 1 whole. We can also multiply, and we can multiply a fraction times a whole number. Hey, by the way, do you realize that this 14 is also a rational number? Because 14 can be written as 14/1. So you know what? As it turns out, all of those integers, -3, -2, -1, 0, 1, 2, 3, and so on, they're all rational numbers because you can put them over 1. Okay, so by realizing that we could also have these fraction numbers that aren't integers, we've got a lot more numbers available to us. And so we actually went along our history just happily with these rational numbers. In fact, along comes our buddy Pythagoras. Most of you guys have heard of Pythagoras, and the date that we have here is about 569 BC to about 475 BC. Been a long time ago. And in the case of Mr. Pythagoras, he and his followers happen to believe that all magnitudes are commensurable. What? Well, essentially, what he thought and his followers were that all numbers could be written as rational numbers. Well, then something happened. Now, we're not sure exactly what happened. Some people will say that it was this that came along. I've got a nice little square. He's a 1 by 1, pretty simple figure. And then you know that Pythagoras and his buddies figured out then how they could find out how long that diagonal is. Right? Pythagoras? Well, this happens to be the square root of 2 long. And square root of 2 is not a rational number. It's a really pretty easy proof. I'm not going to take the time to do it right now, but if you want to email me, I'll give you some information about how we know square root of 2 is not a rational number. Now, technically, by definition, a rational number is any number that can be written in the form P over Q, where P and Q are both integers. So there's no nice fraction that I can write for that. Because I know somebody might be saying, well, I can make that a fraction, square root of 2 over 1. That doesn't count. Now, some people think that perhaps it was that square in his diagonal that made Pythagoras and his followers figure this out. Some people believe that it might have been this: x squared minus x minus 1. Now, I kind of doubt that they knew the quadratic formula at this point in time. And I apologize because I don't have all of my history just as strong as I should. But if I solve this equation, I end up with opposite of b plus or minus the square root of b squared minus 4ac, which ends up being a 5, all over 2 times a, which is 2. And, in fact, if we take, there are 2 numbers sitting here, if you know how to read this plus or minus. And some people believe, I don't need that x equals. Some people believe that perhaps Pythagoras and his followers first came upon this particular number, which is also well known as phi. Okay? So I don't know that there's any final answer at this point in time as to which one they originally came up with, but it just blew a hole in everything, because several of their theorems were built upon this idea that all numbers were rational. So once they found out that that wasn't true, it just blew a hole in their arguments. Okay? Now, the folklore, you might want to go checking. Supposedly, someone out of the secret society of Pythagoras leaked the information that they discovered these numbers. Now, there's 2 versions of what happened to this young man. One is that he was actually killed. The other one is that there was a statue erected in his honor as if he were dead, and everybody just ignored him for the rest of his life. But whichever way it happened, it wasn't good. Okay? So it was quite a scandal, and you might want to do some reading to get more information. But what this did is this brought along the irrational numbers. Because, you know, all the other ones were rational, and it's kind of an interesting word choice here. It's almost like there's a judgment going on here. These are irrational numbers. Hey, there's a few other really famous irrational numbers. You've got pi, which it takes a little bit of work to prove that he is irrational, and it took mathematicians hundreds of years to do it. E is an irrational number. You could have all of these square roots. You could have the cube root of 17 is an irrational number. You could have a decimal like 0.01, 001, 0001. And it just continues on with that pattern forever. Notice it's not repeating, because as it turns out, all repeating decimals are rational. And you actually find out in a late lesson how you might be able to get that fraction for your repeating decimal. But in this case, it's not repeating, there's just a pattern. It's never ending, never repeating. So those are the irrationals. And then what that meant is you take all those rationals and all those irrationals, and combined it gives us the real numbers. So by Pythagoras' time, around 500 BC, we should have all real numbers. Now, I don't know if they've connected them to the number line yet. In one of the lessons we talk about, actually the first one I think, we talk about Descartes taking that number line and turning it into a graphing system, and that number line has every real number. It has every integer, it has every rational, every fraction, it has all of these crazy irrational numbers on it. It's very rich. Okay? So now we're up to about 500 BC. Hey, let's do a little bit of practicing of the arithmetic of these irrationals, because you see, when it comes to arithmetic with fractions, I know you might have forgotten, but I'm pretty certain you've had lots of practice. But these you may or may not have had practice, okay? So, first thing I'd like to do is simplify some of these irrational numbers. Now, I have a crazy way of doing this. It dawned on me that it's a good idea to factor. So I'm going to take 50 and I'm going to factor him down into his prime factors. Well, he happens to be 5 times 10, and 10 is 5 times 2. Okay? And then it dawned on me that I'm really looking for pairs of numbers. Now, here's why it kind of dawned on me. What's the square root of 4? Just the principal square root. You know it's 2. Why is it 2? Because 2 times 2 is 4. Okay. What's the square root of 49? The square root of 49 is 7. Why? Because 7 times 7. If I asked you to explain what does this symbol mean, you would probably tell me I'm looking for what times itself equals that number. Yes, that means you're looking for a pair of numbers. Well, with this number 50, I look at that and I say, well, there isn't a number, not a nice one, which times itself equals 50. That's why I have to write it with this notation, and it's an irrational number. In fact, can you approximate it for me, the square root of 50? Well, you know, that's just above 49, so it'd be about 7.1 maybe, yeah? Okay, but I can actually simplify this a little bit, because if I break it down into its prime factors, I notice that I have a pair of 5s underneath there. And in my distorted brain of teaching high school and college for years and years and years, I thought, well, you know, it's kind of like dating. If you have 2 that are alike on the inside, they get to go outside on a date. And that little 2 doesn't have a date, so he has to stay home. Isn't that cute? And if 2 people go out on a date, we often call them a couple. So on the outside, it's a 5. I know, it's really sophomoric. I apologize, but hey, it works. The idea is I'm looking for what times itself. Well, 5 times itself. So the square root of 50 is actually equal to 5 times the square root of 2. And there are reasons why we want to simplify these, maybe so that we can combine some radicals together. Or for old people like me, I can approximate that now really nicely because I know that square root of 2 is about 1.414. Okay? Now, with this idea in mind, how about the square root of 72? Well, let's see here. 72 is what, 9 times 8? 9 is 3 times 3. And 8 is 2 times 4. And 4 is 2 times 2. Now, I'm doing this rather quickly. If you'd like, you can make a tree. You know how you make a factor tree and keep breaking it down? And I look in there and I say, oh, look, there's a pair of 3s. They can go out on a date. There's a pair of 2s. They can go out on a date. That 2 doesn't have a date. He has to stay in the house. And you'll see everything there is multiplication. So on the outside, I have 3 times 2, which is 6. So the square root of 72 is equal to 6 times square root of 2. Hey, and by the way, just as an interesting reason why I would do this, I can't add these guys, square root of 50 and square root of 72. They're not like. But 5 square root of 2 plus 6 square root of 2, I can add those. I'd get 11 square root of 2. So there's a reason why I might be interested in doing this. Okay. Well, let me give myself a little bit of space here. Now you notice that there's a little bit of a change. I still have this radical sign, but now there's this little 3 tucked down into that corner. Now this 3 is called the index. The index. And that means that this has an index of 3. We do refer to him as the cube root or the third root. Hey, these guys both have an index, but us lazy mathematicians don't write it. It really has an index of 2. We just don't write it when it's a 2. But if it's anything other than a 2, we have to write it. So essentially, this index tells you how many like factors you're going to be searching for. Now, for example, do you happen to know what the cube root of 8 happens to equal? I'm hoping you might realize that that guy is 2. Why? Because 8 is 2 times 2 times 2. So 3 on the inside came out as 1 on the outside. Okay? So with that in mind, that index tells you again how many like factors you're looking for. So here I have the cube root of 24 is 6 times 4. 6 is 2 times 3. 4 is 2 times 2. And you say, do I have 3 of anything in there? Yeah, I have 3 2's. So these 3 2's can all come together. They can be bundled up and brought out. So I have a 2 on the outside, and this 3 does not have anybody to get bundled up with to go out, so the 3 stays inside. 2 radical 3, or I'm sorry, 2 cube root of 3. Now, I went ahead and put this guy on just to make sure that we're all together on what these indices mean. If I have the 5th root of 96 and I'm supposed to simplify that, we don't do that much, but we might. It means that I'm looking for 5 identical factors. Now let's see here. 96, I'm going to take this really slowly, would be 2 times 48. 48 is 2 times 24. 24 is 2 times 12, which is 2 times 6, which is 2 times 3. Hey, if you want to double check my arithmetic, multiply all that together, we should have 96. So do I have 5 like factors in there? I do. I can bundle them all up, bring out a 2, and leave this 3 on the inside. Sorry, I know you're seeing a lot of 2's and 3's, but I think you can understand these powers can get very large very quickly. Okay? So that's just doing some simplifying. And then let's do just a teensy bit of addition and subtraction of these irrationals. So as we look at this, this just looks like an awful mess. But you know, there's an algebra background that you have that might make you think, hey, those are kind of like terms. For example, do you realize that if I have 500 and I have 60, I can actually add those up, but I still have to keep in mind essentially that it's 5 hundreds and 6 tens. I can't combine that and say it's 11 of something, okay? They have to be like. Whereas if I have 500 plus 600, that's 1100. So you actually have been adding up like terms with numbers for a very long time. So I can add these two together and say, well, I've got 1 of whatever that mess is and 7 of that same mess. That gives me 8 times the cube root of 2. Okay? And then I see, well, here's a square root of 5 and here's 11 square root of 5. That would combine to give me, oh, wait, this is a negative. I've got negative 1, a plus 11. That would give me plus 10 radical 5. And they're combined. And then I have a plus 3. And that plus 3 cannot get added with anything else because they're not like terms. So in the case of addition and subtraction, just think of your algebra training and think of having like terms. They are like if they have the same index, and this part underneath is called the radicand. So they need identical indices and identical radicands. Okay. Oh, multiplication. Well, this is kind of scary. But when you look at that, that should be kind of reminiscent of something you've seen in algebra. Doesn't it kind of make you think of foiling? Yeah. And you know what? Guess what? You actually foiled when you took 23 times 12. Because you took the 2 times each of those, you took the 1 times each of those. Here was your first times first. Here are your outers and inners that are going to get added up. Here's your last times last. You've been doing foiling for a very long time. So we're essentially going to foil these as well. So first times first, I'd get square root of 12 because I can actually multiply what's underneath those radicals together. Then I'm going to have minus square root of 2. Then I have plus 3 square root of 6, and I have minus 3. Now let's do a little bit of cleaning up if we can. The square root of 12 can actually be simplified. He is 2 times 2 times 3, so it becomes 2 square root of 3 minus square root of 2 plus 3 square root of 6 minus 3. And you'll look at that and say, am I done? Yeah. None of these have the same radicand. They are all indices of 2, but you cannot combine them because those radicands are different. So that's where you have to leave that mess. Okay. On this next guy, we have 5 square root of 15 times 7 square root of 6. These are actually multiplied on. So I can use the commutative property of multiplication to rearrange this and have 5 times 7 times the square root of 15 times the square root of 6. And these guys, you know, that's 35. And then these can be multiplied together underneath the radical. Now I know 15 times 6 is 90, but let's not multiply those together. Because 90 is a rather large number, and I bet I can simplify this. So that would be 3 times 5, that's my 15, and that's 3 times 2. Now my index is 2. It's not written, but it's understood to be a 2, which means I'm looking for a pair of numbers. Those 3's can go out. Now, when they come out here, again, everything here is multiplied. So you have 3 times 35, and then the 5 times 2 inside is the square root of 10. Wow. You might need to do some practicing with these if you've never really worked with them before. Now this last guy I just kind of put because I wanted to be honorary. We do not have the same indices. So you look at that and say, well, she said we can't do that. Yeah? We do have the same radicand though. So here's what I'd like to do. I can't really work with that effectively in the radical notation. Now, by the way, we have learned algorithms. One algorithm is foiling. One algorithm is that long division process. We could come up with an algorithm for multiplying with different indices. We could. But the easier route to go here is to realize that these radicals can be rewritten as exponentials. What? That cube root is the same as the 1/3 power. And that's actually pretty important in some cases with calculators, because in some cases with calculators, you have to use the fractional exponent in order to get the roots. In fact, let me put another definition over here. A to the m over n power like what do we mean by a fractional exponent? Is the nth root of a to the n. So you can see that that denominator is going to be that index. So in this case, I have an exponent of 1/3, and I have an exponent of 1/2. And then if you ponder, while it's kind of ugly, it's the same problem as having, say, 12 to the 4th times 12 to the 5th. You know you just add those exponents. Okay. So what do I get when I add 1/3 and 1/2? Well, I think it's 5/6. Wow. I actually can multiply those two grotesque numbers. And you could leave it as 12 to the 5/6, or we could use our definition over here, and we could turn this into the 6th root of 12 to the 5th. And that guy would simplify down, but I don't want to take the time to do it. Because, by the way, you might realize I'm looking for 6 like factors, and 12 has 2 2's as factors. So there's actually 10 2's in there. Are you with me? That's kind of crazy. All right. But you've at least got a basic idea of doing some of the arithmetic with our irrationals. Now, the last operation that we usually talk about is division. And these first two are here to keep you from making some bad mistakes. When you see square root of 50 over 10, sometimes students think, I'll just cancel. And I will just knock out that and that, and I'll get square root of 5. No. If you double check what the square root of 5 is, and you double check what this is, no. Because you've got to understand that that is not 50. Remember, that number is just slightly more than 7. Do not cancel a number inside the radical with a number outside the radical. That is totally illegal. Now here's what I can do. We simplified this guy to 2 square root, how about 5 square root of 2? To 5 square root of 2. That's what the square root of 50 is. And then when you're looking at it in this form, you say, oh, look, the 5 is a factor of the numerator, and 5 is also a factor of the denominator. They're both outside numbers, so I can cancel, and I get square root of 2 over 2. Now, by the way, watch what happened here. I had to actually bring out whatever could come out of that radical, and then I was able to cancel. Now, look, I've got 2's, but one is inside, one is outside. Don't cancel them. Hey, just to get a better feel for it, this guy's about a 1.4 divided by 2. This is about 0.7, just about 707. Now, if you go back to the very beginning, take the square root of 50 divided by 10, you should see that we have the same result. And that might help you feel a little bit more comfortable that, yes, that's what was happening. Okay? Now, this next guy, you can actually cancel because they're both numbers underneath the radical. In fact, we have a theorem that says that you can essentially take the square root of 50 over 2. Because they were originally both underneath the radical, I can do this, and I end up with the square root of 25, which is 5. Now, you might say, I don't like that idea. Okay, here's another option. This simplifies to 5 square root of 2. And you can cancel your square root of 2's, and you get 5. So there's 2 really good ways that you could look at that, but my point was, here, do not cancel. Here, because they're both underneath a radical with the index of 2, I can, in fact, cancel. Okay? Now, this last one. If you have never seen this before, I don't think I'm going to make you comfortable because I'm not going to do lots of practice with this. But anytime I see two numbers down here in this denominator, and one of them's irrational, by the way, since this guy is irrational and I'm adding 1, that whole denominator is irrational. There is a specific way in order to clean this up, okay? And it's called rationalizing the denominator, okay? And as I said, if you've never done this before, I don't think I'm going to make you feel comfortable with just one example. So you might want to ask for some more help if you need it. What I do is I multiply by what is called the conjugate. The conjugate is the same two terms, only you change the sign between the two terms. If it's plus, you make it minus. If it's minus, you make it plus. Now, this is only legal if I multiply the top of the fraction by the same thing. Okay? Now, that gives me 4 times square root of 2 minus 1. Yes, I know I could distribute that, but it's not a good idea yet. Okay? Now, in the denominator, if you look carefully, you might realize, oh, that's a lot like the one on the previous screen. I need to use FOIL. And first times first gives you 2. Outers and inners will cancel, and I get a minus 1. That's the whole reason for using the conjugate, because that will happen. First times first, outers and inners cancel. Last times last, you're going to lose your radical, and you're going to, you're basically going to lose your radical. Now, this process only works if the index is 2. If the index is 3, you have to do it differently. Well, 2 minus 1 is 1, so I get 4 times square root of 2 minus 1. And I don't care if you multiply that through or not. But that's the answer that I would get from that division. I know. Some of those irrationals can get a little bit tough. Now remember, we started all of this in the time of Pythagoras, right? And Pythagoras was around 500 BC. Okay. Oh, so then what about the square root of negative 9? And you say, well, Pythagoras knew about square roots. Yeah, they discovered that. But they didn't much like this, so they totally ignored it. And in fact, it was totally ignored for a very, very long time. And along came a guy by the name of Girolamo Cardano, which, by the way, he's an interesting character. You might want to check out the history on him. Kind of considered to be a very mean and nasty guy. But he was very good at solving equations, and he figured out how to solve some cubic equations. And in his work, he came upon these guys, and he pretty much decided, just don't want to deal with those. I don't see purpose in it. And by the way, notice the date. We're in the 1500s at this point in time. Well, about the same time, just slightly younger than him, is a guy by the name of Raphael Bombelli. And Raphael Bombelli says, well, okay, it might be a total waste of time, but I want to go ahead and figure out how to work with these. Okay? So, we're going to go ahead and do some of the work, which Bombelli didn't use this notation, but he kind of got us started on doing some of the arithmetic. But as we continue just a teeny bit with the history, along comes one of the greats of mathematics, Leonhard Euler. And he's done the 1700s. And by the way, all these pictures came from Mac Tudor, History of Math. And old Leonhard Euler kind of figured that these are pretty important, these imaginary numbers. They are going to have to be dealt with. And if my history isn't wrong, he's the one that actually called them imaginary. And it's kind of cool that you've got real numbers. I don't know who called them the real numbers, but we have all those real numbers. And if they're not real, I guess they're imaginary. But we work with them anyhow. And a guy by the name of Carl Gauss also decided these are pretty important numbers. Okay? Now let's go back here. So what about the square root of -9? Well, you realize you got a problem here. Because you might say, oh, the square root of -9 is -3. But wait a minute. What do you get when you take -3 times -3? You get +9. Okay, so there's no way that you can take a number times itself and get a negative. You know that whole how we multiply positives and negatives? Now that's in the real numbers. So what they decided to do somewhere along the way here is this. That square root of -9 is going to be -1 times 3 times 3. And I'm going to bring that 3 out because I've got a pair of 3's. 3 times the square root of -1. And I'm not sure who actually decided that we would call this I. And eventually we all decided that that I is a number. He's the basis of the complex number system, the imaginaries. And in fact, we now have the imaginary numbers, which gets us into all complex numbers. Okay? So, square root of -50. Well, that would be the square root of -1 times 2 times 5 times 5. You know, we've simplified him before. And we do everything else the same. We've got the 5's coming out. And then we let this, we could say 5 square root of -1 times square root of 2. I know that's a little bit crazy the way I wrote it, but I wanted you to see it that way so you knew this was 5i square root of 2. And as soon as you see that I in mathematics, you know, oh, that's the imaginary number square root of -1. Okay? Well, we can add and subtract these numbers because you know mathematicians, we love to add, subtract, multiply, and divide, right? We get a new critter, that's what we do. Your algebra training takes care of you here. You know that this subtraction in front of the parentheses needs to be distributed through, right? And then we'd have 3 plus the -4 gives us -1. 2i plus 9i is 11i. And that would be my answer. This is called the real part because there's not an I attached to him. And this is the imaginary part. And in fact, all of your complex numbers are of the form a plus bi, where a and b are real numbers, okay? And so you have a real part and an imaginary part, and you cannot combine those. Now, the last guy that I have down here for arithmetic, well, no, I have two, I think, is to do this multiplication. And I think that as you look at it, you're going to again think, you know, that kind of looks like foiling again, doesn't it? Absolutely. First times first gives me a 3. Outers gives me a -15i. Inners gives me a plus 2i. And last times last gives me -10i squared. Okay, now, you know you can combine those. You've been combining like terms for years. And you may think you're done, except I squared. If I is equal to the square root of -1, then I squared would be the square root of -1 times the square root of -1. And believe it or not, those two -1s are coming out. We get a -1. So this is actually -1 So I get 3 minus 13i plus 10, because that's a minus 10 times a negative 1. I actually get 13 minus 13i. Hey, another guy that did a lot of work with the complex numbers, and if you get a chance, oh, you really want to work with de Moivre's theorem, some very cool stuff. Hey, you know what? I think I'll leave you with this guy to do on your own if you'd like. You're essentially going to what I call realify the denominator, because you're going to multiply by the conjugate 1 plus I, because we don't want to leave that imaginary number down in the denominator. And of course, that's only acceptable if you also multiply the top. So that's kind of an ugly problem. I'll let you play with that if you'd like. Okay? Now, to recap what's going on here with our numbers, because by this point in time, we have got all complex numbers. And what I find really interesting for those of you that are history people, you know, maybe there will be more numbers discovered. We knew lots of them up until 500 BC. 500 BC, we figure out that they're square roots, cube roots, and so forth. And then it's not until the 1500s, 1600s, 1700s we start dealing with these complex numbers. So maybe in our future we have some more numbers that will come about. Okay? But right now, all the numbers we know are complex numbers. And those complex numbers can be broken down into two distinct sets. Every complex number is either a real number, like the ones we've known for centuries and millennia, or they're imaginary numbers. Okay? And the imaginary numbers bring up our buddy I. Now, the imaginary numbers, we don't do much as far as subsets. You can do a little bit, but in the case of the real numbers, I want you to remember from previous classes that every real number is either irrational or he's rational. Okay? Every number on that number line is one of the two. Now, the rational numbers, that's everything that can be written as a fraction. There are some subsets that we like to work with. There's one subset which is called the integers. And of course, that's where we don't have any fractions or decimals. But we do allow negative numbers. And a subset of the integers is that set of whole numbers. And you might remember that the whole numbers don't have the negatives. They have 0 and all the positives. And then the last guy, the set of natural numbers, which is also called the counting numbers. And that's a succinct idea of what we know now on numbers. Now, you might need to go looking for some more practice on some of that work with the rationals and with the imaginaries, because they can be tough. And I didn't really plan this as I'm going to definitely teach you. Hopefully, I'm going to brush up some of your previous knowledge. Okay, so be sure to contact your instructor if you have some more questions on this. Thanks, and see ya.